So first of all, let's remember that the prepaid forward on the zero of interest is the value of that same maturity zero at time t. This is sensible. This is the prepaid forward at time little t for delivery at time capital T. So the prepaid forward says this is how much it costs you to buy a security which at time capital T will become the zero coupon bond we desire. Well, obviously, if at time little t we buy the zero coupon bond that matures at time capital T plus S, at time capital T it'll be the bond we desire. So that's correct. And then we look at the prepaid forward price of the constant K. This is just the present value of K, which we can express as K P of T T. It's the present value of K dollars at time capital T as of time little t. So now if we take the log ratio of these two prepaid forwards, which I'll just simplify notation FP to FP, but in the numerator we use the prepaid forward of the 0, and in the other one, in the denominator, the prepaid forward of the K. Then what we get is this is equal to the log of P of T plus S divided by P of T T. Because the K, the log of a product, is a sum of the logs that has a constant, and I can throw away the constant because I'm going to calculate a variance in a second. So we do also have from the denominator a minus log of K, but in a moment we're going to throw that away when we do the variance, so we can forget it right now. And notice that this, as we saw in an earlier slide, if I take the ratio of today's price of a zero coupon bond that matures at time capital T plus S and divide that by today's price of a zero coupon bond that matures at time capital T, that is indeed the forward price today for a zero coupon bond P of T plus S. So the log ratio is the forward price with a constant attached, so when we have the variance, we get the variance formula we want, namely that the variance of the log of the ratios of those prepaid forwards is nothing more than the variance of the log of the forward prices. So if we have any assumed distribution for the forward prices of this zero coupon bond, that'll give us the sigma squared that we need. So what Black did was to assume that the bond forward price is log normally distributed and has a volatility of sigma. So in other words, we'll assume that there's a log normal distribution for these forward prices. And with that, he derived at this expression for the value of this call option, a call on F, and remember what F is the forward value. So we're going to, we have a call, it's an exchange option. It's a call on this risky asset and with a price of K, and it's equal to F, the prepaid forward is the coefficient of ND1, K is the coefficient of ND2. But what's important to note is that all the parameters in that calculation can be based on today's yield curve. And the reason for that is if I multiply P0T, the price today of a T-period bond, 0, times F, I'm actually getting the price today of a T plus S period 0. So P times F in that expression is a price I can observe today, requires no model. And of course, P0T is a price I observe today. So the advantage of this model, and this is an application of the exchange rate model, it's a present value of these future prices, is that all the parameters in this formula, P0T times F, that's a price today of the T plus S period 0, and K is a constant, and P0T is known. And then I can calculate the log of the forward price. This forward price is also observable. We have a formula for that based on today's prices of zeros. So all of this formula, by making the assumption that the forward price of these zero contracts are log normally distributed, log normal because we don't want negative prices, so a log normal distribution is a reasonable assumption. And we'll assume that they have a constant volatility of sigma. With those reasonable assumptions, we get the value of this call on a zero coupon bond, and it's all parameters that we can identify easily in today's market.